All right, so what is it? Connor, we are sad that you're not here, by the way. I guess I'll leave you a secret special bonus word worth candy at the end of the lesson. I'll like whisper it into the microphone so even Jake and Akshay, I don't know. All right, but I shifted some of the homeworks, as you see, because obviously we didn't get into 412 yesterday, and now Connor's not here. So we probably will only make it to 414 this week. But today, we are factoring with area models. So yesterday, we figured out some interesting things, or we started to figure out some interesting things. One more. There we go. So we had written this down, right? Because we were discussing the area as a sum and the area as a product. And we said the diamonds deal with area, or not area, sorry, sums and products. We didn't really connect it to anything. And then Casey, right, our teammate, quote unquote, Casey realized, hey, these green things when multiplied equal the same thing as the yellow and blue things, and it worked for all of these situations. All right, so let's continue to investigate this. So we've developed a pattern, but the question here is it useful? Can we apply it, or is it just like, oh, well, that's cool, right? Like a squared plus b squared equals c squared, cool relationship, also extremely useful for solving unknown pieces of a right triangle. The whole diagonal products being equal here, we got to figure out, is it useful? Is it applicable? So this one, does it fit here? Like, what's 35 times 4? 140. And of course, x times x is x squared. X squared times no x's is still x squared. Okay. So let's go ahead and write this out as the, like the pieces that we've been talking about, right? The area written as a product and as a sum. So take a moment and copy this onto your graph paper. And then we're going to write it out and put the like terms together. Factoring with area models. You do not need to apologize for asking. Sorry, I just across the hallway they clapped and I felt like we should clap. I'm finally getting back into my normal habits. And like one of them was having a binder for all of my classes, not having to switch between 3 different binders. Like you guys in your mega binder. So, yours or mine? So I'll say I have many large binders. So when we write this out, it's still 401. I'm on the wrong page. I'm going to guess that this is potentially 5x, but I'm not sure yet. But if that's 5x, then this would be 2x, negative 2, negative 7, and that all works. Just because I saw the 10 and the 35, right, in my head I was thinking like, all right, well 5 is probably a good bet. So our area as the factored out binomials hey, I know that you're waiting for the demonesthesis room, but what else you're doing is distracting me in my class, so 10x squared plus how many total x's? Ooh, crap, it's minus. Or it's a negative amount at least. I guess I can do negative. 39. 39. Weird number. Plus 14. So what we're trying to develop here is a way that we could start with the cubic trinomial, or sorry, the quadratic trinomial, because it only has power 2, right? That's quadratic. And break it up into that factored form. What's the hardest part of, like, if we think about going backwards from here to here to factor this thing? You're handed a trinomial, they say factor it out into the binomials.
The hardest part is splitting up the negative 39x.
The hardest part is splitting up the negative 39x. And what Casey said was, if I draw one of these rectangle things, we know that there's this relationship. What doesn't get split up?
10x squared and 14.
Yeah, like the a, x squared, and the c, right? So we put those in there. The difficult part is the other boxes.
Yeah, and then we know that.
But Casey's pattern told us that if we know this, what does that let us do?
It shows us that the opposite sides are supposed to also multiply.
So if what I highlighted in yellow is equal to what we highlight in blue, then we know if this is 140 x squared, then this is 140 x squared.
Then you just have to find a way to get that.
So okay, you said you just have to find a way to get that, which that should be a bad word in our classroom also. So we know this, but that's not just what we need to force to happen. There's something else that has to happen here. So you just said, there's no great notation for these because this is A, that's C, and these are parts of B, right? So I'm going to say B1 and B2, although we're definitely not talking about trapezoid bases. So let's just B1 and B2, right? What do we know about B1 and B2, aside from the fact that we just said they have to multiply to make 140x squared?
They have to add to, they have to sum to negative 39x.
So B1 plus B2 equals what now?
30, negative 30. So then you could do those diamond.
I think I have.
My alarm's going off from yesterday's schedule.
Hold up.
Yesterday we were done with class right now. Except we still didn't go to lunch in a very good time.
Couldn't you make those diamond things?
I don't know, you're talking with Jake. Is that minus?
Yeah.
Okay, just checking.
Oh, yeah, never mind.
There we go. That's why I was just checking.
Yeah, I did that wrong.
I should have like a little timer so like each of you gets like 30 seconds at the board at a time or something. That feels overly complicated. I mean, I think everything you wrote up there is right, but that feels very
So
complicated.
then we can solve for B2.
Oh, can we?
Yeah, because it's written clear.
And that's like easily solvable.
No.
Okay. Well, I'm not gonna do it. Do you want to do it?
Not really.
Well, mathematics is all about finding the route that we want to take, not like the ugliest, most dangerous route possible.
Yeah.
You can change the thickness of your ink, by the way. Yeah, I was about to say that might be necessary at this point. So in the diamond problems, what goes in top?
Isn't it the
Product, right?
Yeah.
Wow, she's just starting over. We're just giving up.
OCD.
It was too thick.
Yeah.
Didn't like it.
The other part.
The fact that you're using red is surprising too. Flip that color palette. Choose whatever color you want. If it's too bright, it's a little hard to see. Connor's gonna watch the video and be like, "Great, I'm watching the video to watch Akshay pick thickness and color."
That's also going to annoy me.
That's not bothersome to your OCD.
No, it is, but I'm just dealing with it because I don't want to waste time.
It's like therapy, right? It's like exposure therapy. You have to deal with it and just like let it go. Because this is what we said we need to make happen. We need to make them sum to the b value and multiply to the value of a times c.
Yeah.
So let's on our paper really quickly. Do me a favor. Just so we can write down some rules. So we said when we set up, this is not specific to this problem, right? So if you want to scooch down your paper to somewhere that you can write like a general rule, we're saying in this rectangle, we have A here and C here unless you build it differently. And in the diamond, we're going to have A times C in the top part, whatever we call that, and B. So what I would also write down is a reminder of ax squared plus bx plus c. So if given a trinomial, we are saying that we're going to multiply a and c, and you bring the x squared with you. And in this situation, actually I wrote down for us, that becomes 140x squared, negative 39x.
So the diamond problem, instead of trying to draw a diamond like you did, I just draw an X.
Yeah, that's fine.
Yeah, I do an X.
That's fine.
I know.
So we know negative, right? Because to add to make a negative and multiply to make a positive, that's one thing that we can go ahead and just fill in right away. What about like 30 and 9? Actually, here's a really good trick. If you started with 38 and 1, give me your eyes up here real quick, because I know you're deep in thought. If you start with 38 and 1, what do we get when we multiply? 38, really small, way too small, right? So if you want to be dramatic, jump to the most middle. What's the most middle values that would sum to 39? 19 and 20, right? And that's way too big. So that tells me we can't be right in the middle, can't be right at the end. So go to the middle of those things, right? If we're thinking about like the factors of, I mean, we can either think about the factors or what are the pieces that add up to something? Do we have a vocab word for that? I think they're the add-ins, aren't they? So 30 and 9, 18, that'd be like 270. How? I don't know, play with some options on your paper.
Well, I think we already know what it is.
You could also think through the factors of 140 and see what sums to 39, because the factors of 140 might be a little bit easier. So like,
I'm sure we already know what it is, though.
Yeah, but like, let's say we didn't know what it was. So then we
I thought it was 35 and 4.
oh, is it?
Yes, negative 35 and negative 4.
Oh, yeah, because this is probably already know the answer to.
yeah. But like,
Ah, so make sure you put the x there. Make sure you put the x there. So that works. All right, let's try this on one that we don't know. 2x squared plus 5x plus 3. Go ahead and write it down. One trick here, a cannot be 0, because then it's not a quadratic. I shouldn't use the word trick, but I also don't like the rule, or the word rule. Go ahead and try that. I'm gonna go to a different slide so I can copy this down differently. 2x squared plus 5x plus 3. So if we draw our rectangle, we know 2x and we know 3, or 2x squared and we know 3. So if we draw our diamond that we said we're all going to start kind of cheating with how we draw the diamond. That was really fast. Holy cow.
It's x plus 1 times 2x plus 3.
Wait, so you said 2x and 3x then? Is what goes here? So then, does it matter where I put the 2x and the 3x?
Not really.
Not really, because my other numbers can move around too. So then if that's the case, 2 probably goes here, right, with a 3 here.
And then x and 1.
Yeah, and then we don't really want to change anything, so we just have x and 1, so that one looks real weird. So, yeah, 2x plus 3. X plus 1. All right. That seemed a little too E-word.
Simple.
So, Miguel says, all right, let's do this. Well, let's get some bigger numbers, right? That was probably easy because they were small numbers. 3x squared plus 10x plus 8. Miguel sets up 3x squared and 8. The next thing he's going to do is figure out, after we've set up the 3x and the 8, what's the next thing we do with our numbers? Yeah, so multiply them together and we get 24x. And we know on bottom here is going to go two numbers that make 10 but also make 24.
64.
This is why this technique is so convenient. Our brains are trained to think about numbers and like put them together and like 6 and 4. So
3x times 4, or 3x plus 4 times x plus 2.
double check that it all works. And yeah, there we go. Epic. All right, so Kelly, what should Kelly put on top here?
She should put 12x squared and then 7 on the bottom. X and then you get 3 and 4. Yay!
Look how fast that is. So then, where does it feel like I should put the 3x?
It does not matter.
It doesn't matter, but sometimes it's nicer if I put it here because here is then all even, right? So it's just a little nicer to say, okay, so if I put 2x here, then this is 2, and then this is 3, and this is 1x, and that all makes sense, right? Like, it's that puzzle building. All right. I copied the same page a couple times. Try this on your own, little bigger numbers. What's 6 times 12? Ooh, 72 and 17. That's some interesting numbers. Connor, your secret code word is purple aardvark.
I mean, you can just go on his page and watch the video.
It's true. Okay, 3 equals 4 times 2 equals 3.
What goes in the side boxes? You're jumping over the steps here.
9x
9x and 9 and 8. So guys, that same technique of like, if you're way too far away, like bring your numbers closer together or further apart, right, when we're thinking about factors. So then, now is there a way to jump over this? Like, I know we're working pretty fast, but 6x squared, 12. I'm going to go ahead and put the 9x here just because 3's, but again, it doesn't really matter. Probably 3x, and then probably 2x, which then means 3, 4. Does it all work? Yeah. So what I'm wondering is, this feels like a 3-step process, right? And I need you guys to, again, know, all because I ask a question doesn't actually mean that it has an answer. That doesn't mean this question doesn't have an answer. I just want to put it out there again.
Thanks for the mixed message.
That was like last night, Mrs. Gordon was like, I think we should meet with these students for conferences. But then again, a conference may not do any good, so maybe we shouldn't meet. I was like, wait, what? Can we skip the diamond or can we skip the rectangle? Or do we kind of need both to like work together?
I mean, for now, it's easier to use.
I think we can skip the rectangle.
How do you think we can...
Actually, no.
What's the rectangle do for us that the diamond doesn't?
It shows us what the binomials are.
Yeah, it shows the broken up binomials, right? What's the diamond do for us that the rectangle doesn't really?
It shows what
Finds those B pieces, right? So, I mean, and I like how you said it, right now it's easier to use both things together. I don't know if there's a way that we can not use one or the other. Right now, we're using both. Who what?
the FOIL method.
What's the FOIL method?
I don't remember, but
I don't know what you're talking about.
yeah, don't you
My
guys
FOIL
know?
method is normally pull out about an inch or two too much so you can wrap around the dish. I have... Oh, crap, where is it? I have a laugh button.
You
Yeah, but I forget where it went. When I make bad jokes.
do? I mean, I
You
actually
should
laugh.
pull it out, and then every time you make a bad joke, you just...
I normally do. Where did it go? So upset now. I'm just now realizing the things that I haven't seen in the past 2 months. Like that binder. Alright, I'll try to find it by tomorrow. When I make bad jokes.
Is it like the easy button for laugh?
Yes.
My grandparents used to have an easy button, and even when broken, you drag them down to that thing.
Oh, that was easy.
First, outer, inner, left.
Oh, okay. I got confused, so I was like, wait, further guidance normally comes at the end of the lesson. Try all 4 of these. So the habit that I would kind of get into right now is when you approach one of these, I would just start, and this is why I asked you the questions I just asked you. I would just start by doing this and this. And you don't need to draw the diamond. I like the make it easier, do the X. And then fill in your A and your C, right? Because we said we agreed on all that.
3x and 6x.
Ooh, faster than Jake.
X plus 3 times x plus 6.
Yeah, but that one was easy, let's admit. It was a 1x squared one. So do B, C, and D. And then I'll probably just have to be content with only covering one lesson. Since Connor's not here, we'll just wait. Now guys, in this class, I tend to have to do less of this. When I was in school, right? Way back when. Back in like the aughts. It was 2000 something, and it was the aughts. We got taught FOIL, right? Yes, I know FOIL. Oh my gosh, Mr. Hudson's been lying to us. And how we would solve quadratics is to do this and then say, well, if I had 4x and x, outer, inner, last, check, 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 doesn't work. What if I have 2x and 2x, outer and last and inner and check, 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 check. Ah, I finally found, like, it was this whole guess and check process. No one ever showed us the technique that we figured out here, right? No one ever, like, let us know. And all my love to my high school math teacher, for real, he's probably why I became a math teacher. But they didn't know to teach us stuff like this. Like, we hadn't figured out these convenient little tricks. So now we can right here throw a negative 60x squared. Down here throw a, which feels like those numbers oddly interact. But actually 10 and 7 isn't that far off from what I want.
It's 20x and negative 3x.
And back in our, like when I was in school, all we would have known is like, if we got to multiply to make a negative and add to make a positive, one needs to be negative and one needs to be positive, but which is which? We just had to try everything like a bajillion times. True confession, I hated quadratics. Hated them. It wasn't mathematical to me. I was like, this is a guess and get it wrong, and then try again process. This is mathematics, right? We recognized a pattern. We tried it out, right? We made a conjecture. We said, we think this works. We've tried it out. It hasn't failed yet. It's pretty darn convenient. This is sweet. I now love quadratics. Sorry, Mr. McCulley. Used to hate them. Now I love them because this is nice. I'm going to guess the 20 would be nicer here because the 4 and the negative 3x here. So did you guys do 2x's? Well, that wouldn't really make sense with the 3 here.
I did 4x.
So 4x makes more sense to us, and if that fails, we can try something else. But if that's 4x, then this is
5.
and if that's 5, then this is, and if that's negative 3, then that's just x. And it works! I don't have to guess, check, or get anything wrong. Quadratics make me feel dumb. Like, for real, when we were doing this sort of process, and like, I'm going to see my buddy Randy tonight. He's an architect. He works north of here, so a lot of times he stops by and says hi. He likes playing with my dogs. So, I'm going to bring this up to him and bring up, like, our math class and show him this technique, and I bet it's going to blow his brain. Like, he's going to be floored by how efficient this is. So let's try another tough one. It doesn't have to be super big numbers to be tough. And tough doesn't mean, like, bad or, like, impossible. It just means, like, it's not super easy. 4x squared, 3, 12x squared, negative 8x. No, this is C. I mean, you guys probably already did it, but the sum is negative, the product is Ooh. How can we sum negative and positive product? 2 negatives, right?
And
Oh, and
it's 6 and 2.
it's 6 and 2. Because our brain is good at recognizing number patterns. I really don't think it matters where you put these. I mean, it doesn't. We already agreed it doesn't, but sometimes it's nicer than other times. Are there potentially 2 different arrangements of binomials that can get us the same answer?
Isn't that 12x squared?
Yeah?
It's 1 minus 2x times 3 minus 2x.
1 minus 2x.
Instead of negative 2x plus 1.
Isn't this supposed to be 12x squared instead of 4x? Or
Yes.
no, never mind. No, never mind.
I really appreciate you pointing that out. Those are the trapdoors with this technique. Is accidentally forgetting what goes where. Remember, A goes here, C goes here, product of A and C goes on top. And then B goes on bottom. Here's my question. Does this still work?
I think it's work. It's negative 2x and 1 and negative 2x and 3.
Oh, you made your B's negative.
And then the 1 is plus.
Even though I set that rectangle up differently, will the binomials come out differently? No. It'd just be down here, right? And then, yeah, they're the same. Sorry, that's negative 2x. Interesting. So even the different arrangements of the rectangles, different ways to get to 4x, right? Take 2 different routes, can still get to the same place. And our final one here, and then I'll leave you guys be so we can do our homework. What goes in the bottom left?
3x squared.
Top right. Ooh, interesting. Got a positive value, negative value. Over here.
Negative 9x
And then 5.
5x. I'm thinking 3 and 2, but that doesn't work.
I don't think this is true.
Now, we never made a rule about whole numbers, right, or integer numbers. But I'm like, we haven't used any partial numbers yet.
Right. So I don't think
use fractions. Fractions are dumb in this kind of stuff.
Fractions are kind of dumb. How did we determine yesterday that something quote unquote wasn't factorable? What are we? Why are we doing this? Why are we drawing the rectangle?
so we know what the binomial is.
Yeah, but like, why did we make it a rectangle? Why didn't we just like make it a square? Why didn't we, I don't know, like any other shape? Or like why, and why do we keep calling this an area model?
Because it shows area. Oh, we can make it with algebra tiles.
It shows area. Why do we think this one might fail if we think about the area model? What's different here than in the other ones that we've been solving
It does
today?
not work.
Huh?
It does not work.
But why?
The amount of x's is not a multiple of the x squared. They all need to have a common factor for it to be factorable.
I agree with what you're saying. I'm kind of hinting towards something else. I agree with what you said, though. I just kind of want us to.
Like 5 would have to be a 6 for it to work.
So this is not an even number, but it is just 1. So if we think about how this looks, we would have our x squared, and then there's some number of x tiles, and there could also be some number of x tiles. And then here, what's up here?
18.
Yeah, that's your constant, right? What do we think is bad about D that makes it fail?
The constant has to be even in this scenario.
Constant doesn't, we just had an odd constant here, we had a negative constant here. So 3x squared could arrange like that. Or, I don't know, I lost my x squared. It could arrange like this. Right, I mean, or we could stack them vertically, I guess.
But that's just a rotation.
Yeah. So, up here, if I had like 3 x's, we'd be good with no constants. But when we have 5 x's, what we're saying
You need
is,
to have -2 or 2.
so something here isn't right, is what
I
we're
was
saying?
gonna say,
Sit down, Mr. Hudson. Give me the pen.
if you put these,
Oh, over on the other side? Ah. Oh, that's
then we would be good with 2 for the constant. But we don't have 2 for the constant.
so the numbers like just don't work together.
Yeah.
Guys, here's these silly. It like feels so simple. It feels silly. You can't make a rectangle with those. With 3 x squared tiles, 5 x's, and 3 -1 tiles, you can't make a rectangle. It just doesn't work. So it just doesn't work. That's it. There's no like special secret until we make it work. So what you're saying is this doesn't work. Notice I always ask questions until I can say what you're saying. What you're saying is this doesn't work because things don't work out nicely. And you have a conjecture that if we mess with the constant, so you said do that, do this and this. So you want to make the constant into a 2. And actually, they'd like us better if we did this. I know it doesn't look as pretty. But then it keeps our area model, right? All right, so I agree. So how could we make that into a 2? How could we make the constant into a 2?
Add 5.
Yeah, let's do it. I want to fix this. Do you guys not want to fix it?
Add 5 to everything.
Crap, wait.
It's not an equation.
Ooh. Is it not, though? What does quadratic mean?
There's 4 things that.
That's not what it means. Google. What's quadratic mean? I'm going to race you by getting out the textbook but doing it slowly.
Involving the second and no higher power of an unknown quantity or base. A quadratic equation.
have x cubed or higher.
Quadratic equation. Any equation where at least one term has degree 2 and no term has degree higher than 2. A one-variable quadratic equation can be written in standard form, ax squared plus bx plus c, where a, b, and c are real numbers and non-zero. For example, 3x squared minus 4x plus 7.5 equals 0.
Does the quadratic have to equal 0?
Where'd I go? Right here.
The quadratic formula states that ax squared plus bx plus c equals 0 and a cannot equal 0.
But quadratic expression
See, that's what I was
tells us
talking
this right
about.
here. But quadratic So wait, if we want to make this an equation, we can just make it equal to 0?
That's what I said yesterday. No one
Hold
listened
up.
to me, but that's
It's not that I wouldn't listen to you.
because no one else
It's that we weren't ready to discuss that part of this lesson yet. So wait! If we set this equal to 0, I know we're out
Then
of
we can
time.
add 5.
I know we're out of time, but hold on.
So then we get 3x squared plus 5x minus or plus 2 equals 5.
Okay.
And then we can solve for x times x squared.
I bet we can, but we're out of time. I'll see you guys tomorrow. That's leaving them on the hook right there. I don't know, guys. I think we're on to something.
Yeah.
Hold on just a second, 'cause I'm going to stop my recording.